In lab yesterday, you guys were looking at Newton's law of motion, and we didn't call it that, but we were actually looking at Newton's second law. And what we all investigated collectively was how force, mass, and acceleration are all related. Now remember, a force is a push or pull. Acceleration is how fast velocity changes. How fast velocity changes. Okay? And then finally, mass, which we have in the past defined as the amount of matter in an object. That definition is true, but it is also a measure of inertia. Now remember, inertia is the tendency of an object to resist a change in its motion. Okay? So we're looking for the relationship between force, push or pull, acceleration, how fast velocity changes, and mass, which measures inertia or resistance to change. Okay? So keep that in mind. What we probably realize, and I think what we saw from lab, is if you make this force bigger, if you pull on the object harder, then the acceleration gets faster as long as the mass remains constant. And some of you tested, well, what happens if we leave the force constant and make the mass bigger? Well, if the mass increases, then it has a greater resistance to change, and that force is less able to accelerate the object. Newton was the one who put this all together, and he came up with what we call Newton's second law of motion. And what Newton's second law says is it says that the net force acting on an object is equal to the mass times the acceleration. Net force equals mass times acceleration. A lot of times you'll see this written as acceleration is equal to net force divided by mass. Okay, those are equivalent forms, they're the same equation. I want you to think about what this means. This means if I have a really, really big force, if this side of my fraction is big, then my acceleration is big. If I have a really, really big mass, if the denominator is big, then my acceleration is going to be small, which makes sense. Bigger objects are harder to change their motion. They don't resist motion anymore, they resist a change in motion. Okay? With Newton's second law, we're actually able to predict what's going to happen to an object if we know the force and we know the mass. So this allows us, like the cart actually had a mass, an empty cart without anything in it, just its wheels being pulled this way. This thing has a mass of 500 grams, and that's 0.5 kilograms, and that's something we should remember. Mass, in the past we've measured small masses, we measured it in grams. Now we want to measure in kilograms. And the reason we measure it in kilograms is because of the definition of a newton. 1 newton is the amount of force required to accelerate 1 kilogram of mass at 1 meter per second per second. Okay. 1 newton is the amount of force required to accelerate 1 kilogram of mass at 1 meter per second per second. So if we have 500 or 0.500 kilograms, that is 0.5 kilograms, that's 500 grams, but we do want to leave it in kilograms. So that cart had a mass of half a kilogram or 0.5 kilograms, and we were pulling on it with a force of around 5 newtons. Well, somewhere between 1 and 5 newtons. Okay. Let's see what the difference is. If I pull on, I'm going to redraw my picture. Okay? If we have this cart, it's sitting on the track, and we pull on it with a force of 1 newton, and its mass is 0.5 kilograms, what's its acceleration going to be? Well, acceleration is net force divided by mass. Since there's only one force on it, 1 newton divided by 0.5 kilograms is equal to 2 meters per second, or 2 meters per second squared. If we pull on it with 5 newtons of force, so instead of 1, we do 5, then my acceleration is equal to net force divided by mass, that is 5 newtons divided by 0.5 kilograms, and this is equal to 10 meters per second per second. Okay, so 5 times as much force, 5 times its acceleration. You'll notice this does not mean the object's moving at 2 meters per second or at 10 meters per second. It's getting faster at that rate. We actually didn't have carts that were quite 0.5 kilograms because we had other things on them. But this is how we use Newton's second law. All we have to do is we have to find the net force, we have to find the mass, and we can find the acceleration. We can also use it in other ways. If I want to know how much force is required to accelerate an 800 kilogram car at, say, 3 meters per second per second. How would I do that? Well, I know my mass is 800. I know the acceleration is 3 meters per second, and I know I'm looking for how much force that's going to take. So the net force is equal to mass times acceleration. That's Newton's second law. So I'm going to take 800 times 3, which is equal to 2400 newtons. Okay? That's a big number. That's okay. Forces can be really, really small. Forces can be big. It depends on if we have big objects or small objects. It depends on if we have large accelerations or small accelerations. Okay? So Newton's second law, not a super tricky equation. We've used these things before. Remember, net force is the total force. So if you have an object that's actually got sort of a tug of war going on, so sometimes we'll have something pulling this way with 25 newtons of force, and maybe there's 5 newtons of friction that's opposing that motion, and this thing has a mass of 5 kilograms, and I want its acceleration. Then you're going to say, well, net force equals mass times acceleration. Right here it tells me my mass equals 5 kilograms, and I need to get the net force. Well, the net force is the sum of all those forces. I have 25 newtons to the right minus 5 newtons to the left is 20 newtons to the right. So my net force is 20 newtons, and so I'm going to take 20, set it equal to mass 5 times A, divide both sides by 5, and I get an acceleration of 4 meters per second per second. So Newton's second law, not too tricky.